Okay, so hello everyone. Joseph and Dami took us to very theoretical things. Let me bring us back to some more practical issues, but take you a little bit to the field of communication and do some statistical analysis over there. So I want to talk about routing. Routing is, of course, very complicated and not necessarily all of it is related to signal processing, but we'll talk about a very small part of the routing. So if everyone here is not familiar with routing, just in 2 words, routing is about finding a path in a network. What you have over here is one of the maps of the internet. It's very, very complicated. The routing algorithm needs to find a path for each packet who needs to go over there, and as you all know, the internet and the billions of packets that go over here every day, it can be quite complicated, especially that we need to consider constraints like the network throughput, the delay, reliability, balancing of the load so that no point will be overloaded. And all of this is typically done in a distributed manner, which becomes a very, very challenging task. We will not work on the internet. We are interested in wireless networks. Luckily, wireless networks are typically smaller, so the problems are smaller. On the other hand, we have 2 new challenges. The first one of those is that nodes move. Unfortunately, they move, and that means that we cannot just learn a map of the network connectivity. We need to update it all the time. If we plan to route a packet through some specific route, it might have changed in the time that passed. We need to always relearn the map of the network, which of course make the routing very, very complicated. So we will limit ourselves to the simplest form of routing that I know of, which is geographical routing. In geographical routing, we simply assume that each node knows its location. Probably it has a GPS or some other mechanism, but it knows its location, and through a very small amount of communication, it knows also the locations of its neighborhood. And what it does, it knows that it needs to transfer a packet from the source here to some destination in a known location. It doesn't bother itself with all of the path from the source to the destination, but only on the next hop. What will be the next stage to transfer this packet? And what it tries to do is to take the packet forward toward the destination, hoping that there will be a route in the continuation of the path. So we will limit ourselves to this type of geographical routing, which solves us all of the mobility issue. But there is another issue. And the other issue in interference in wireless networks is interference. Now, in wireless networks, we know that each transmission causes interference to all other receivers in the network. And probably not all of the possible links in the networks, links that could be sustained alone, can be sustained simultaneously. Now, this complicates the routing or the connectivity map in a very much, because now it's not enough to know that I can reach a node from another node. If I really want to do optimal routing, I need to consider which pairs of nodes can exist together, which triplets of nodes can exist together, and just trying to keep up the information of what sets of links can be sustained together is a very complicated task. So we have a whole range of possible algorithms here. If we try to do optimal solution, we need to consider all of the possible set of links that can be sustained together, and then try to choose the best path. This is, of course, very, very complicated, and although there are works who consider that, there is no network who actually implements that. What we can do is limit ourselves, limit our knowledge of the network, try to collect less knowledge, and then we don't need to use it, and then we have much simpler algorithms. If we take it all the way down, we can simply ignore the interference. What do we mean by ignoring interference? We just worry about where we can go. What is the connectivity map of the network? Which packet can go to another link? And then we will let the MAC, the Medium Access Protocol, to handle the interference. We will talk about it a little bit later. But it can be done. Of course, it is far from optimal. We want to do something which is a little bit better. We want to still limit our knowledge of the network only to our neighborhood, only to know where we are, of course, where the packet needs to arrive, and then where are our neighbors and what is the channel from the source, us as a source, to each possible destination. And then we assume that we do not know if our neighborhood or any other node in the network will be active or not, which means that we cannot actually optimize based on the interference. We do not know if there will be interference or not. What we assume is that the node activity and the location of the nodes in the whole network is random. So the interference for us is random, and we do not ignore the interference, we just address its statistical nature. So we wish to average, to maximize the average network throughput. So instead of ignoring interference, which is far from optimal, or taking into account all the interference, which is very complicated, we take into account only the statistical nature of the interference. Of course, there are several works who address this type of problem. The main one, which actually used statistical signal, stochastic geometry, are these two. The first one says, I will route each packet to the nearest edge in a cone. For example, if I know that this is my source and the destination is somewhere in the right, I have a parameter which defines a cone. Now I only look for the node which is closest to me within the cone. Why to route to the closest node? I know that I will not gain much progress by routing to the closest node, but I will probably not create much interference because I only transmit to a very short distance. On the other way, I can say that I want to make the most progress within each hop. If I want to make the most progress, of course, I can transmit very far if I have enough power, but then I will create very strong interference. So what I do, I have one parameter, which is a maximal radius for transmission. And then within this radius, I choose the node which gives me the most progress, meaning that the projection of the distance over the x-axis is maximal. Doing that, I'm trying to take the most out of each hop, but of course I'm limited by the radius, so again, I will be somewhere in this cone, so there is some similarity between these two algorithms. Now, what is the advantages of these algorithms? First of all, we have a routing algorithm. It is only characterized by a single parameter. So once we know the optimal value of the parameter, the routing is very simple. And what they've shown is that they can give, although not exactly closed form, but they can give a performance analysis of this, of the average throughput in each case. And they can find the optimal value of this parameter. So that's a good thing. We have good routing. What is the disadvantages? Well, first of all, it's not a good approach for an optimization problem to first give the solution and then just optimize the parameters. We want to find the optimal solution from the problem and not invent it. And the other thing is that it doesn't account for channel parameters. For example, we will consider here only fading in the simplest case, but what happens here? I have two nodes. If I know that the fading for this node here is much, much better than the fading for this node here, there is a point that I need to prefer going further away because I have a better channel for it. This algorithm doesn't help me to do it. So I'm looking for a better algorithm. So what is our network model? If Ami tried to convince you that geodesic convexity is a big thing, the main thing that I want to convince you is that modeling networks with a random process, a random point process, is very useful, and we can do a lot of things in communication and in signal processing by such a modeling. We will consider only a Poisson point process. Now, a Poisson point process is just a generalization of the regular Poisson process to 2 dimensions. And if I want the simplest definition for it, it is taking any area A, and what we need to have is that the number of nodes in such an area will be distributed Poissonly with a parameter which is lambda, which is called the density, multiplied by the area A. From this definition, we have many, many useful properties. For example, if we take any 2 areas, A and B, which do not have any common area, then the distribution of nodes in area A and distribution of nodes in area B is completely independent. More intuitively, maybe, if we take any area A, and I will tell you the number of nodes in this area, then the nodes are distributed uniformly in this area, uniformly and independently from each other in this area. So basically, this is a very intuitive model for networks, or actually for the distribution of things that we do not know much about them. When we want to work on networks, we have 2 possibilities. Either we take a specific network and do something about it, or we need to find some model some statistical model for this network. Now, usually when you go to network guys or to communication guys and tell them, okay, what about statistical model for your network? It's very difficult to find such a model. This model basically is the closest thing that we have to saying that we do not know much. We have some area, everything is IID, everything is distributed uniformly, but it's only an infinite area. So we need to take the Poisson point process to define it. The network now is characterized only by a single parameter, which is the density of nodes. So it's very convenient for modeling. It's also very convenient mathematically. We have very, very useful properties of the Poisson process. For example, any scaling of a Poisson point process is a Poisson point process. Addition of any 2 Poisson point process is a Poisson point process. Shifting of any point, even a random independent shifting of any point in a Poisson point process is a Poisson point process. So we have many, many mathematical tools that help us analyze such type of networks. Now, this only tells us what is the location of the nodes in the plane. What we need now is to start building the communication over it. And we assume we have 2 layers. First, we need a medium access control, which we take, again, the simplest protocol existing, which is the Aloha network or slotted Aloha network, which means that we divide the time into slots, and in each slot, each node decides completely independently of any other slots, but in a random way, whether to transmit or not. So all the transmissions are independent. And what's important here is that if a transmission fails, then it will be retransmitted at a later time. The combination of random transmissions, which means that the network does not stay constant, but we have change due to this randomness, and the retransmissions allows us to produce a very robust algorithm that can handle even cases of interference through transmission at a later time. So this is a very simple algorithm, and yet it allows communication in a very robust way. And more and very usefully for us, the random activation of nodes means that the active nodes are still a Poisson point process. Now putting the physical layer over it and not going into how much time I have. So going into the details. What we have here is just what is the received power at each node from each transmitter in the network. We said that only part of the nodes will transmit, the other ones will be receivers, and the received power is combined by only 3 components. This is the transmission power, rho. It depends, of course, on the distance between the transmitter and receiver, with an alpha here, which is the channel decay factor, usually between 3 and 4. And we have fading, random fading, which we mentioned earlier. Now, using the Shannon formula for a Gaussian codebook, we know that we can transfer a rate. On a single hop, we can transfer a rate which is log of 1 plus the signal to interference plus noise ratio. Here we don't have noise, we don't need it. We are limited enough by the interference in the network. So this is the signal to interference ratio, and this is the rate that is achievable on a single hop. Most importantly is what is our performance measure. First of all, we cannot actually measure throughput because we consider an infinite network, so we have an infinite throughput. Instead of throughput, we consider throughput density, meaning that we consider, for example, the throughput of a receiver in a unit area. This is given here by the density of the transmitters. Now, we need to consider the fact that we are dividing the transmission into hops. So if we have a link of 2 kilometers and we divided it into hops of around 200 meters, we will need 10 transmissions to transfer 1 packet. And then what we do is take the progress here, delta, which is the projection of the distance made over the direction to the destination, and divide the average progress by the average link length, where a link length is from the initial source to the final destination. And of course, we have the rate. In the continuation, we will remove this number, the average link length. We will just take as a performance metric the nominator in here. So our performance metric depends on the rate that we transfer and the distance for which we transfer each packet. And now when we want to analyze the network, we take just a snapshot of the network. In this snapshot, we do not know where is the actual sources of packets and where are the actual destinations. What we know is that we have some active transmitters. Each one is going to transmit a packet to a nearby neighbor, and we know the directions that each packet needs to go. Now we know that the choice to transmit is independent between this transmission. Also, due to our mechanism, the routing decision itself will also be independent between these transmissions. And of course, the space is homogeneous. Yes?
You know the location of the destination?
I know the location of the destination, yes. That's the thing that is easiest in here. The packet comes with the location of the destination. And as the space is homogeneous, we take one receiver to be the probe receiver. And now we have to consider only 2 things. What is the rate achieved on this link to this probe receiver, and what is the interference created by all other transmissions. To simplify things even further, we use a power control or inverse channel power control, meaning that the transmission power is set so that the received power is always 1. This is a simplifying assumption. We can do it up to a constant, but we allow ourselves to let it be exactly 1. Doing that, the rate on the desired link is completely independent of the routing decision on this link, because the desired channel gain is exactly 1. But our choice will affect all other links. Now, doing the statistical geometry, the stochastic geometry analysis, and we have, for example, a poster outside that you can see that shows this analysis, we can show that the rate, the average throughput, depends on these routing decisions only through this expectation here. So if we know the expectation of the square of the distance multiplied by the fading value to the power of -2 over alpha, then we know the effect of all routing decisions on the throughput. And then we can restate our optimization problem, which was basically to maximize this expectation here, using the independence. This is the multiplication of 2 different expectations. And as we said that the rate is independent of the routing, we can take the expectation of the rate outside of the internal maximization, and given conditioning on the value of this expectation, we have the routing depending only on this expectation here. Now, maximizing a conditional expectation given the condition is not so complicated. Using Lagrange multipliers, we wish the best routing decision will be the one that will maximize this expectation here, which is the progress of this. Okay. The progress of the resulting from this decision, routing decision, minus the expectation of the routing decisions of all other users in the network. And the last thing that we have here is that through the homogeneous of the plane, the distribution of all other users is exactly the same as my distribution. So I can change the variable here from the distribution of another random interferer to myself. And then I have a very, very simple metric for routing, which is take just the progress of, for each node that I'm considering, take the progress and minus a constant, which is the Lagrange multiplier, multiplied by this value that represents the average interference effect of the network. And I don't have much time, and it's good because I'm toward the end, so let's show you a result. Down here is the routing performance of the 2 algorithms that we mentioned earlier. Up here is what we can achieve with this optimal routing, which is, of course, much better. Remember that it's not only the routing that is much better. These routing algorithms weren't that bad. They were optimized. But here we can use the channel fading. Our routing will prefer channels with nodes with good channel fading, so we can gain much more. So to conclude, we presented a completely novel approach to derive routing decision, a routing metric, which is actually, we do not present an algorithm and then optimize it, but we actually find the optimal routing decision for a specific scenario. We can take the physical layer parameters into account to achieve better routing. Of course, it is better than other results. Very importantly, as we only generated a metric, although it was for a very simple routing algorithm, this metric can be combined with other routing protocols, which are for more complicated routing approaches, and can produce very interesting other results, which we are now working on. And that's all. Thank you.